Alright folks, I just want to talk about counting a little bit more, do a few example problems. Counting can get quite tricky, so the more example problems you see, the better. Here is one fact I want to tell you guys. And in some sense, it's a definition, but you can prove it using some high-powered mathematics. But in some situations, you might see something like 0 factorial. And you can think, well, what does that mean? Is it 0? Actually, it makes most sense to define it as 1. And you could think of it this way. If you think of it as the number of ways of arranging 0 things, then of course there's only one way of arranging 0 things. You can't do anything. So 0 factorial we define as 1. So that'll come up a little bit throughout these exercises, potentially. But it's good to know. So let's do this example. So again, by words, I just mean any arrangement of letters. So how many 7-letter words are there where the letters, in fact, we'll do 2 things. So the first one will be the letters are in alphabetical order. And the second will be, well, the letters are in alphabetical order, and let's say P is the middle letter. And let's just be clear. I don't want any repeat letters. So if I use the letter once, then I can't use it again. So this is a good problem to think about. That'll help you with thinking about good ways of approaching counting problems. Well, one way you could approach it, I'll talk about an incorrect approach first. Well, you could say, well, the first letter, there's basically, you could think like 26 choices for it. But then, your second letter really depends on what your first letter is. If I pick A, I have 25 choices for the second letter. But if I pick something along the lines of maybe S, well, I have something like, I don't know, 6 or 7 choices. So you'd have to deal with each case independently. And that would be really tough. So this is no good. This isn't a good approach. So maybe if we think about how we literally would do this, it would help us come up with a good way of determining the best way of counting. Well, if we were to do this, what would we do? Well, we would pick the 7 letters from the alphabet, and then we would just put them in alphabetical order. So in some sense, the order that I pick the letters doesn't matter. There's only 2 states for the letters to be in. Either they get picked or they don't get picked. Because once they get picked, I'm going to put them in alphabetical order later. So that's kind of the key to this, is put the letters in alphabetical order after they're picked. So we really just need to pick 7 letters out of 26. So this is one of those combination problems. So I'll just use the notation we're looking for 26, choose 7. So remember, that means there are 26 things in total, and the 2 states are picked, and 19 will be not picked. So let's go ahead and do that. So that's going to be, well, 26 factorial over 7 factorial times 19 factorial. 7 picked, 19 not picked. Say there are 7. You can imagine check marks for picked, X's for not picked. Any arrangement of those 7 check marks and 19 X's will give you a new word in alphabetical order. And you could simplify this if you would like, but I'll just tell you that it is 657,800. So that one wasn't too bad. Let's look at the next part. Again, with a lot of counting problems, it's all about coming up with an approach that works. Sometimes approaches, while they could be correct, the problem would be so intractable because you'd have to deal with so many cases that it's not a good way of approaching it. So let's look at the second one. So again, same idea, but we know the middle letter is going to be P. Well, how can we think about this? Well, one way to do it again is we can look at this as two separate words in alphabetical order, but we're only allowed to use the letters from A to O here. And here, we're allowed to use the letters from Q to Z. So this is kind of two separate problems in one. So we need to figure out how many 3-letter words we can make in alphabetical order with the letters from A to O. I'll tell you that there's 15 letters there. And how many 3-letter words we can make in alphabetical order using the letters from Q to Z. And I'll tell you that there are 10 letters there. So 15 plus 10 is 25, plus the P is 26. We've accounted for all 26 letters, so it looks good. And so our plan will be, we'll pick one of these 3-letter words from A to O and one of these 3-letter words from Q to Z. So once we figure out these counts, we're going to multiply them. It's like an ordered pair type thing. So when you're thinking, if it's like an ordered pair problem or an ordered tuple problem in general, then you multiply these things. It's like a Cartesian product. So let's go ahead. So the first bit we're looking for is 15, choose 3. Because we have 15 letters from A to O, and then we're choosing 3 of them and not choosing 15 minus 3, which is 12 of them. And over here, we're looking for 10. Choose 3, which is, well, 10 letters in total, so 10 factorial. We're choosing 3, and we're not choosing the other 10 minus 3, which is 7. We're going to multiply these. Let's simplify this a little bit. So this is 15 times 14 times 13 times 12 factorial, but that 12 factorial is going to cancel with this 12 factorial. Maybe I'll write that in. And I'll write this as 3 times 2 times 1 times 12 factorial. Those guys cancel. And then let's try and find some other factors for everything in the bottom. So I can pull out a factor of 3 from the 15. So that becomes a 5. And the 2 I can pull out from the 14. That becomes a 7. So this becomes 5 times 7 times 13. We can calculate that in a second. And over here, same idea. So this is going to be 10 times 9 times 8 times 7 factorial over 3 times 2 times 1 times 7 factorial. 7 factorials cancel. Look for common factors. Take out a 3 out of the 9. Take out a 2 out of the 8. So this is 10 times 3 times 4, which is of course 120. So this is 120. 5 times 7 times 13 is 35 times 13. This is 105 plus 35, which is 455. So whatever 455 times 120 is, let's just do it. So that's 0. That is, what's that going to be, 9, 10. And then this is 455. We add, we get 6, 4, 5. So the number of 7-letter words in alphabetical order that have a P in the middle is 54,600, which is pretty cool. So again, the key to this whole thing is realizing the best way to think about the problem is you pick the letters. The order you pick them doesn't matter because you're going to put them in alphabetical order after the fact. And again, for part B, you just have to look at it as 2 sub-problems. So alphabetical order from A to O and alphabetical order from Q to Z, and they're 3-letter words each. All right, let's do the following example. So poker hands consists of 5 cards out of 52. And all the cards are different. They have a value, so from ace to king, there's 13 values, and one of the 4 suits, the suits are hearts, diamonds, clubs, or spades. So 13 times 4 is 52 cards in total. So my first question is, how many poker hands are there? And the second one, it should be an A there. The second one is, how many contain exactly, let's say 2 face cards. Okay, so let's do it. Well, again, the order that you receive cards in a poker hand doesn't matter. You just get 5 cards, it doesn't matter. So what are we doing? There are 52 cards in total. We're choosing 5, and the other 52 minus 5, which is 47, are not chosen. So again, if you have 52 letters, 5 of which are, say, C for chosen, 47 are X's for not chosen, any arrangement of those will give you a new poker hand if you give some sort of order to the 52 cards. Maybe you say the ace of hearts is card 1, the 2 of hearts is card 2, the 3 of hearts is card 3, etc. If you come up with some order for the cards, then any arrangement of those 47 X's and 5 C's gives you a new poker hand. And of course, this is 52. Question A. 52 to choose 5. Which is, well, that's going to be 52 factorial over 5 factorial times 47 factorial. And I will just tell you guys that is 2,598,960. Okay, let me write that on the next line. That's a little small. 2,598,960. Great. Now, let's look at question B. So how many contain exactly 2 face cards? Well, let's think about this. This is almost 2 problems in one. So what are we going to do? So we pick 3 non-face cards out of... Well, let's talk about the face cards first. And we're going to pick 2 face cards out of... Well, how many face cards are there? Well, as a reminder, there's a Jack, Queen, and King of hearts, diamonds, spades, and clubs. Forgive my poor drawings, but this is a Cartesian product question. We have 3 types of face cards for suits, so there are 12 face cards, which means that there are the rest, the other 40, are non-face cards. So I'll put an and here as well to remind us we need to do both. 3 face cards out of 40 and 2 face cards out of 12. So that's what we're doing here. Okay. So in some sense, we can just write down our answer now. So we're choosing, out of the 40 non-face cards, we're choosing 3 of them for our hand. And we also need to choose, out of the 12 face cards, 2 of them. So let's simplify this a little bit. So this is 40 factorial over 3 factorial, 37 factorial, 3 chosen, 37 not chosen out of the 40, times 12 factorial over 2 factorial, 2 chosen, 10 factorial, 10 not chosen. All right, and again, and here's something. When you see kind of the number you're choosing either be really big or really small compared to the number of things that you have, you know there's going to be lots of simplification you can do. So 40 choose 3, well, I'm going to get 40 times 39 times 38, and everything 37, 36, all the way down is going to cancel out with 37 factorial, and then I can cancel the factors from my 3 factorial. So this is going to be just like the previous questions, 40 times 39 times 38 over 3 times 2 times 1, which I can cancel out. And over here we're going to get 12 times 11 over, oh, there's no times there, over 2 times 1. So let's simplify this as much as we can. I see a factor of 3 in 39. That becomes 13. I see a factor of 2 in, say, 38. That becomes 19. Okay. And over here, I see a factor of 2 in 12. So that becomes 6. So this becomes 40 times 13 times 19 times 6 times 11. So, calculating that, we get that 652,080 poker hands have exactly 2 face cards. Again, kind of all the actual thinking and work goes into this answer here. Everything past that is just some simplification. So, in some sense, unless explicitly told in a question, if you left your answer like this, I would be happy. All right, let's explore combinations just a little bit more. So, here's a nice fact. And it is that, I'm going to write this down and I'm going to talk about it. So, n choose 0 plus n choose 1 plus n choose 2 all the way to plus n choose n is 2 to the n. And you could ask yourself, well, how would I show this? And you could do an inductive argument. That would probably work for you. In fact, that would work for sure. But just by thinking about what's going on here, it might be quite obvious. So let me kind of give you a hint. So let's say we have a set A that has the, let me give myself a little more room. Okay, let's say we have a set A that has the elements from 1 to n in there. Well, we know the size of the power set of A, the set of all subsets, well, that's 2 to the n. And if you think about what's going on here, well, let's look at this n choose 2. If we think about this in terms of subsets of set A, well, this is we're choosing two elements in A. We can think of it like that. There's n elements in A, we're choosing 2 of them, and it's the number of ways you can do that. So maybe I'll even put here number of ways of choosing 2 elements in A. And if we choose 2 elements in A, that we can think of it as the number of ways of choosing 2 elements to form a subset of A. So the number of subsets of A of size 2. So this here is the number of subsets of A with size 2. And then similarly, well, if we pick no elements, it's a number of subsets of A with size 0, and we know there's exactly one of those. It's the empty set. These are all the subsets of A with exactly 1 element, so you'd have things like, so this is size 1, so you'd have things like 1 or 2 all the way to n. So there's n of those guys. And if we keep going, we're running through all the numbers from 0 up to n. So that's all possible subsets. And we already know how many there are, and that is 2 to the n. So hopefully this argument shows that this formula is true. And I'll make a quick note. You can also show this by induction. Awesome. And how about another fact? And let me show you this one. So I'll show it to you both algebraically and in terms, well, we call it combinatorially, but just thinking in terms of subsets. So n choose r. So remember that you have n elements, you're choosing r of them and not choosing the other n minus r. So I want to convince you that that's n minus 1, choose r, plus n minus 1, choose r minus 1. So let's show this in two ways. So the first, let's show it algebraically. All right, well, we know what these things are. So let's start with the right-hand side, and let's see if we can make it look like the left-hand side. So we have n minus 1, choose r, plus n minus 1, choose r minus 1. So that's going to be n minus 1 factorial over r factorial, and then n minus 1 minus r factorial. So that's n minus 1, choose r. So we chose r things, and we didn't choose the other n minus 1 minus r things. And then this is going to be n minus 1 factorial over r minus 1 factorial times n. I'll write this out here. This is n minus 1 minus r minus 1, which is n minus 1 minus r plus 1, which is n minus r. So this here is n minus r factorial. And we want it to look like n factorial over r factorial n minus r factorial, choosing r things out of n and not choosing the other n minus r. Okay, so we want to add these. A good thing to do would be get a common denominator, and in fact the common denominator that we're going to get is exactly this guy here. So if we think about it, these guys here, this factorial here, is all the numbers multiplied from 1 all the way up to n minus 1 minus r. Or maybe we could rearrange that a little bit and write it as n minus r minus 1 instead of n minus 1 minus r. Just so you can see it's one less than what we want up here. So we're missing a factor of n minus r to make it look like this denominator. Over here we have the n minus r, but we're missing a factor of r. We have all the numbers from 1 up to r minus 1 multiplied together, so we just need to multiply by r. So let's go ahead and multiply top and bottom of each of these fraction of factorials by what's missing. So I'm going to multiply this by n minus r on top and bottom, and I'm going to multiply this by r on top and bottom. So our numerators become n minus 1 factorial times n minus r over r factorial. And here we have n minus r minus 1 factorial times the next number up, n minus r. This n minus r is 1 greater than n minus r minus 1. So this is just the next number in the sequence. So this is n minus r factorial. Just like if this here was, say, 11, this here would be 12. And 11 factorial times 12 would be 12 factorial. Just an example. Over here, same idea. So this is n minus 1 factorial times r. Well, r minus 1 factorial times r is r factorial. R minus 1 factorial times r is r factorial. And if you can't see that right away, write it out and you'll see it almost immediately if you write out exactly that and write out what r minus 1 factorial is. You'll see exactly what's happening. And we're left with this n minus r factorial. Okay? So let's add these. They have the same denominator. So this is n minus 1 factorial times n minus r plus n minus 1 factorial times r all over what we want, r factorial, n minus r factorial. Now we need to just show that our numerator, or denominator, is good to go. We need to show that this is n factorial. Well, we see a common factor of n minus 1 factorial in both terms, so let's factor that out. And we're left with n minus r plus r over our denominator. And we can see n minus r plus r is just n. So this is n minus 1 factorial times n over r factorial n minus r factorial. And so we have all the numbers from 1 up to n minus 1 multiplied together and then times n. So this is indeed n factorial over r factorial n minus r factorial, which is exactly n choose r. So that's the algebraic way to show that this works. Let's talk about the combinatorial way. Okay, so what's happening here? Let me write down the expression again. N choose r is n minus 1 choose r plus n minus 1 choose r minus 1. And we can think about it. So thinking of it again as subsets of the numbers from 1 to n, this time of size r, these are all subsets, or let's say the number of, oh, what did I do here? The number of all subsets of n, of the numbers from 1 to n, let's do it like that, of size r. So if we think about it, let's write down an example in some sense. And there's kind of this special element n here. So I'm going to circle n. Well, if we think about it, well, if we forget about n, well, maybe your subset doesn't have n in it. So these are the number of subsets of the numbers from 1 to n minus 1 of size r. And these here, well, these are also subsets of 1 to n, right? All the numbers from 1 to n minus 1 are included in 1 to n. So these guys, if we know these guys, we know some of the ones from 1 to n. But the other types of subsets here are going to include n. So these guys here, well, these are the number of subsets of from the numbers from 1 to n minus 1 of size r minus 1. So these ones, well, these are the ones where you could add n to them, and then they would be subsets of size r of the numbers from 1 to n. So you can add n to them to get in the count of the left hand side. And these guys in yellow, these guys are just good to go already. So we're building up. We can think of it as building up subsets of size R in the numbers from 1 to n from subsets of the numbers from 1 to n minus 1. And we look at the ones where we're either good to go, so they already are subsets of the numbers from 1 to n. They have R things, we're good to go. But maybe there's of size R minus 1, and then we just need to add an n to them, and they become what we need over on the left-hand side. So that's the other way of thinking about these. So that's pretty cool. And it's two ways, both algebraic and combinatoric, to think of the same identity, which is really cool. Okay, let's do another problem. So let's show that 2n choose 2 is the same thing as 2 times n choose 2 plus n squared. And having a lot of experience with this, just looking at this problem, I know it's not going to be too difficult. I know it's just going to be fairly straightforward. And the reason I can see that is because I have this quite small r down here. So I'm choosing only 2 things out of 2n. So in the formula for a combination, well, most things are going to cancel, which is nice. And same here. So all these kind of, how many we're choosing out of n and out of 2n is small. So it's going to be nice small expressions I can just deal with algebraically quite easily. So let's go ahead. Let's just write it down and show that it makes sense. So 2n choose 2 is the same as 2n factorial over 2 factorial. We're choosing 2 things, and we're not choosing the other 2n minus 2 things. And we want to write it as the left-hand side, so we know what it needs to look like. So let's simplify this as much as possible. Again, I can cancel off everything but the 2n and the 2n minus 1 with this 2n minus 2 factorial down here. And we're just left with a 2 factorial, which is 2 times 1, which is the same as 2 here. Okay, well, that 2 cancels off there. And look at this expression. It's not too bad so far. All it is n times 2n, n times 2n minus 1. And we know what that is. So this equals 2n squared minus n. Okay, well, we need an n squared, so let's put that to the side. So this is the same as n squared minus n plus n squared. Okay. And now we just need to show that n squared minus n is the same thing as n choose 2 times 2. Well, that's not too bad. N squared minus n is the same as n times n minus 1, just factoring out an n, which is the same as, well, let me write it like this. I'm going to write it like n times n minus 1 over 2 times 2. And we still have this n squared. And the reason I did that is because I know what I want my expression to look like. I know this needs to be n factorial over 2 factorial n minus 2 factorial, which is n times n minus 1 over 2. So I know what this looks like. There it is. So this is the same thing as 2 times n choose 2 plus n squared. So we're done. And so the key to this, just thinking like it's going to be just a simple algebraic manipulation problem, is if you notice these small numbers that you're choosing. If you're choosing small numbers or numbers really close to 2n, if I had instead of a 2, I had a 2n minus 2, well, I'd end up with the same expression here. Choosing 2 things and choosing 2n minus 2 things, you're going to have the same number of things. You're just replacing the ones chosen with the ones not chosen. Maybe that's another fact that's quite easy, is that n choose r is the same thing as n choose n minus r. And basically, you swap your x's and checks in the sense of the word. So you're choosing what you're not choosing, and you're not choosing what you're choosing. So there we go. There's another example. And let's do a couple more. Let's do the following one. So, how many 8-letter words, and we're just going from the regular alphabet, and I just want to be clear, can have repeated letters. So our choices are independent of each other. Choosing something doesn't preclude a choice later down the road. So the first thing is, well, that has exactly 3 vowels. Okay. The second one has no vowels or anything from the set X, Y, Z. The third one is exactly 3 A's and 2 Z's. And the fourth one is exactly 3 vowels where none are adjacent. Now, counting is one of those things where it is all about the approach that you take. You have to be a little bit creative. And if your first approach doesn't work or doesn't seem to be easily calculatable, maybe it's a good idea to try a different approach. Well, let's look at the first question. Well, it has exactly 3 vowels. So, if we think about it, the first thing we have to do is decide where in the word our vowels are. So step 1 is choose where the vowels are. Then once we do that, we choose the appropriate letters or individual letters. Okay. So, the first step, let's call it step I and step double I. So step I, well, we need to choose where the vowels are. If we think about it, we have an 8-letter word, and there has to be vowels somewhere, so maybe here, here, and here, for example, and consonants, which are not vowels, the other places. Any arrangement of those V's and C's gives us new locations for vowels and consonants. So we know how to count that, so the number of places the vowels can be well, there are 8 letters in total. 3 of them are vowels. The other 5, 8 minus 3 of course, are consonants. So we're arranging 3 V's and 5 C's. So this is again a combination. This is in fact 8 choose 3. We're choosing 3 vowels in 8 locations. So this becomes, of course, 8 choose 3, and I'll just tell you that this is 336. So that's part 1. So now that we have, let's say we do that and we choose a location, now we just have to choose the letters. Well, how many choices are there for each of the letters? Well, for each consonant, there's 26 letters in total, 5 vowels. So there are, maybe I'll use a different color, I'll use red. There are 21 consonants to choose, 5 vowels, 21, 5, 5, 21, 21, 21. So, in total, and it doesn't matter where these consonants or vowels are, there's always the same number of choices for them. Remember, our choices here are independent. This is an AND problem. You choose a consonant and a vowel and a consonant and a vowel and a vowel and a consonant and a consonant and a consonant, or in whatever way your word, out of the 336 kind of blueprints for where your consonants and vowels go, you're going to have to choose from 21 consonants 5 times. So number of individual letters, letter choices we'll say, I guess, letter choices. So we pick 21 5 times, since there are 5 consonants and there's 21 choices for your consonants, and you can have repeat choices, and there are 3 vowels and 3 locations for your vowel. There are 5 choices for each vowel in 3 locations. So in total, there are 336 times 21 to the 5 times 5 squared different words in question 1 that satisfy that there are exactly 3 vowels. Okay, that one wasn't too bad. So that was 1. Actually, I should write that this is 2. Okay, so let's do problem 2. So problem 2 says there are no vowels and no letters in X, Y, or Z. So really what it's saying is none of the letters A, E, I, O, U, X, Y, and Z. And there are 8 letters we can't choose. So we're left with, well, 26 minus 8 is 18 choices for each letter. There are no location issues with this. We don't have to choose where the vowels or the consonants or anything like that go. So the number of words, well, just for each letter, we have 18 choices, and there are 8 letters, so we have to make that choice 8 times. So 18 to the 8. All right, the third one says contains exactly 3 A's and 2 Z's. Okay, well, let's think about this. So again, this is going to be in 2 parts. We need to choose the location of the A's and Z's. And then 2 is choose the other letters. All right. So again, actually let me use I for that, since that's what I used before. So for the first bit, again, there are 8 letters. We want exactly 3 A's. We want exactly 2 Z's. And we want, well, the other letters can be anything else. So there are 3 letters left, so 3 more other letters. Okay. So again, any arrangements, you can imagine this being maybe a, let's call it a square, I guess, to mean other letter. Any arrangement of the 3 A's, 2 Z's, and 3 squares gives you a blueprint to build your word. For example, maybe it looked like this. A, Z, 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 square, 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 where the squares are they can be any of the other 24 letters. So that's an example how that would look. Okay, so let's count how many there are. So number of blueprints, I guess, because we'll have to choose what goes in the squares next. Well, we have 8 letters in total. 3 of them are A's, 2 of them are Z's, 3 of them are squares. So, if you simplify this, let me just tell you, 560. So there are 560 different blueprints where our A's, our Z's, and our squares could go. And then secondly, let's scroll up here. Once I choose a blueprint out of the 560, I need to actually put some letters in the squares. So number of individual letter choices. Well, there's no choice for the A's and the Z's, or I should say one choice, A and Z, depending on where they are. So we don't care about those to make individual letter choices. But for the squares, well, each square, we can choose any letter that isn't an A or a Z, because we wanted exactly 2 A's and exactly 3 Z's. So there is 24 letters left, and I need to make that choice of 24 3 times. So 24 cubed different individual letter choices. So in total, there's 560 times 24 cubed different words that have exactly 2 A's and 3 Z's, where the word is 8 letters long. All right, and finally, let's do 4. So this one has 3 vowels, of which no 2 appear next to each other. So this one is going to be in a few parts. So we need to decide where the vowels are in relation to the consonants. So in some sense, a good way of thinking of it, and this is kind of a hard thing, and it's worth maybe stopping the video and thinking if you can come up with a good way of doing this problem. So yeah, pause the video, see if you can think of a good way, even to say where the consonants and vowels go, how many different ways you can do it. Okay, well, you might have tried just counting how many ways there's like that you can start with a vowel and then a consonant, or a consonant and then a vowel, and then a consonant, consonant, vowel. But if you did it like that, I think your choices would be too many to actually count. It would be quite intractable. So a good way of approaching it is thinking, well, I have 4 consonants. Or sorry, 5 consonants. I was saying 4, I meant 5 consonants since there is 8 letters, 3 of them are vowels. So there are 5 consonants. So let's just put them in like this. Now, I definitely need a consonant between each vowel. That's important. You can have 2 consonants together. We don't care about that. But we do care about not having 2 vowels together. So I'm going to think of these as just spaces. So we could have vowels there or not. So we have our 5 consonants. And how many spaces do we have? We have 6 spaces. So we have 6 spaces. So in 3 of them, we're going to have vowels. And in the other 3, let's use V for vowel. And the other 3, we're going to have nothing. It's just going to leave it as a space. So again, if we count the number of 6-letter words where we have 3 V's and 3 N's, that gives you an indication of where in these 6 spaces the 3 vowels go. For example, if I had something like N, let's have the N's here, and then the V's in the other spaces. Well, this corresponds to, because remember, the N we want to represent having nothing there. So this represents the word consonant, vowel, consonant, vowel, consonant, 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 vowel. Thinking of the N's as just nothing, as leaving it blank. So there is our 8-letter word, and we have vowels between the first and second, second and third, and after the 5th consonant. So any arrangement of those N's and V's gives us a new place for our vowels. So let's count how many ways there are to do that. Let me use black. Well, that's going to be, well, we have 6 letters. 3 of them are V's. 3 of them are N's. And you can simplify that. And what you will get is 20. So there are indeed 20 different kind of blueprints for where your vowels can go. That's great. So we have 20 blueprints. Now, once we have our 20 blueprints, we just need to choose what our vowels are and what our consonants are. So the number of individual letters. Well, there are 21 consonants. We have to make that choice 5 times. And there are 5 vowels. We have to make that choice 3 times. So that's the number of individual letters. Once we have one of our 20 blueprints, we have to choose 5 consonants, of which there are 21, and 3 vowels, of which there are 5. So in total, there are 20 times 21 to the 5 times 5 cubed different words where it has 3 vowels, but the vowels can't be next to each other. And again, let me point out what each of these numbers mean. So the 20 is the number of ways you can have your vowels arranged in some sort of blueprint fashion so that they're not next to each other. And that we got by looking at it as you can either have nothing or a vowel between 2 consonants. Here we have a vowel, and here we have nothing, for example. So this corresponds to that, and this corresponds to that, for example. And then, once we pick our blueprint out of the 20, we have to choose 5 consonants, so we have to make a choice out of 21 5 times. Remember, once we use a consonant, we can use it again, so it's just 21 times 21, etc. 5 times. And then there are 5 vowels, and we have to pick the 5 vowels 3 times. Since there are 3 vowels in our word, we have 5 choices for each